In this lesson, you will define the parts of an angle, describe and identify parallel lines, straight angles, transversals, and alternate interior angles, and you will apply and prove the alternate interior angles theorem and its converse. Let's look at the parts of an angle to start. This angle has two rays, ZA and ZU, meet at point Z. Where they meet at point Z, they form a vertex, angle Z. We say rays ZA and ZU, but those rays could also be small snippets out of longer lines that intersected at point Z. They could be snippets cut as rays or as line segments, depending on taking an infinite chunk or a finite chunk of the infinite intersecting lines. Unlike the intersecting rays ZA and ZU, parallel lines never meet. The two lines, line segments, or rays never converge or diverge. The only sneaky way to get an angle from parallel lines is to declare each line is a straight angle, which has a measure of 180 degrees. Parallel lines can be intersected by transversals. Any line cutting across parallel lines is a transversal. It can cross at any angle. A transversal intersecting parallel lines at 90 degrees is perpendicular. When a transversal intersects parallel lines, it creates an interior and exterior. When the transversal intersects, it creates 4 angles at each parallel line, or 8 angles altogether. 4 of those angles are exterior, and 4 are interior. Today we are interested in the 4 interior lines. Those are our alternate interior angles. Let's create parallel lines LI and ON, and a transversal HE. The 2 points where HE crosses the parallel lines are points A and R. You mark drawings of parallel lines with little bird feet marks, like V's on their sides. Notice we have 4 exterior angles: angle HAL, angle HAI, angle ORE, angle NER. And we have 4 interior angles: angle LAR, angle IAR, angle ARO, angle ARN. Today we are only interested in the 4 interior angles. 2 of the interior angles are built using the top parallel line LI, and 2 are built using the bottom parallel line ON. Alternate interior angles are 2 congruent angles from different parallel lines, one from LI, one from ON. This says, angle LAR is an alternate interior angle with angle ARN, and angle IAR is an alternate interior angle with angle ARO. Once you can recognize and break apart the various parts of parallel lines with transversals, you can use the alternate interior angles theorem to speed up your work. The alternate interior angles theorem states that if 2 parallel lines are cut by a transversal, then the pairs of alternate interior angles are congruent. The converse of the theorem is also true. The converse of the alternate interior angles theorem states that if 2 lines are cut by a transversal and the alternate interior angles are congruent, then the lines being cut by the transversal are parallel. Let's prove both of these theorems with our figure. LI and ON are parallel lines, given. Transversed by HE, given. We could declare all sorts of relationships, but the proof can be short and simple. LI is parallel to ON, given. Angle LAR is congruent to angle ORE, corresponding angles postulate. Angle ORE is congruent to angle ARN, vertical angles theorem. Angle LAR is congruent to angle ARN, transitive property of congruence. The transitive property of congruence says, if A is like B and B is like C, then A is like C. Since angle LAR was congruent to angle ORE and angle ORE was congruent to angle ARN, then angle LAR is congruent to angle ARN. To prove the converse, we work the other way around. LI and ON with transversal HE. Given. Angle LAR is congruent to angle ARN. Given. Angle LAR is congruent to angle HAI. Vertical angles theorem. Angle HAI is congruent to angle ARN. Transitive property of congruence. LI is parallel to ON. Converse of corresponding angles theorem. That's it. You can now identify alternate interior angles and can now apply the alternate interior angles theorem.